All right, this is the interim test review. So you have the paper copy. I would like you to try that first and then go through these problems. So the first one is we're going to take these concepts and we're going to come up with examples of these and then maybe a diagram to go along with it. So if we're talking about positive work, this is a force speeds an object up. You can come up with any sort of creative example that you want to. For this diagram, we have the object that is moving in this direction and the force that's pushing it this way. So positive work, that force is with the displacement. And the thought is the force is causing the displacement. For negative work, we're going to have a force that slows the object down. If we're talking about negative work, that would be my object moving in one direction and the force moving backwards, trying to stop it. So here the force is opposite the displacement. For zero work, what we're going to say is that net force is zero on the object, or we're going to say that the force is perpendicular to the motion. If we have net force is zero on the object doesn't speed up or slow down. So we would have a force this way and a force this way that are the same size. And my object still moves forward. So with this, we would have a constant velocity. And then for the force perpendicular to the displacement, our force would be down and our displacement would be this way. That's also going to give me zero work. For law of conservation of energy, a good example is that a ball falls down. When this happens, kinetic energy increases because the ball is going to get faster, and the gravitational potential energy decreases because the ball is losing height. And so for our ball falling down, that's what it looks like. But if we want to look at graphs of stuff, you've got energy as a function of time. Sorry, you have energy. And if you look at the potential energy at the beginning and the kinetic energy at the beginning, so at the top, we have a lot of potential energy and not very much kinetic energy. And if we look at the same thing for the bottom, our potential energy has stopped and our kinetic energy has gotten bigger, but the total mechanical energy is constant. Potential energy, for potential energy, we have MGH, gravitational potential energy. This is stored energy. Here the object is lifted up, so if we take that and we lift it up to a height h, our potential energy is going to have to do with that height of mgh. For kinetic energy is 1/2 mv squared. This is motion energy. Any object in motion has kinetic energy. So we have our mass moving. That thing has kinetic energy. For power, power is work over time. This is the rate that work is done. So the example that we all did is you run up the stairs fast. If you run up the stairs fast, you have power. So going up the stairs, we have that person that, we have that person that ran up the stairs very quickly. Their power was the work they did. So mg, the force that they had when they lifted themselves up, h, the height of the stairs, divided by the time. A person is lifting a 10 Newton bag of groceries to a height of 3 meters for 3 seconds. Calculate the power of the person. This information is the force. 3 meters is the distance. 3 seconds is the time. If I want power, I know that it's work over time. But I also know that work is force times distance. So if I put those two things together, power is force times distance over time. We got 10 newtons times 3 meters divided by 3 seconds, giving me 10 watts for the power. A ball is thrown vertically upward and comes back down. Describe the energy transformations of the ball. Well, it's going to start with kinetic energy. Kinetic energy is going to decrease as the ball moves up. And potential energy increases when the ball stops at the top. Kinetic energy is 0, and we have maximum potential energy. As the ball falls, kinetic energy increases because the ball is speeding up. Potential energy decreases. Draw the energy bar graph of the potential energy and the kinetic energy of the ball. So we'll do 3 different times. We'll do the bottom, and then we'll do the top, and then we'll do the bottom. So the potential energy at the bottom is 0. The kinetic energy at the bottom is full. And then at the top, the potential energy is a maximum. The kinetic energy is 0. And at the bottom, our potential energy has gone away again, and our kinetic energy is back up to the biggest value. And then at all points, mechanical energy is the same. And just to remind you, mechanical energy is kinetic energy plus potential energy. Graph them as functions of time when the ball is thrown up and the ball comes back down. This is a good little graph to have. So we have those 3 points. So if we start off with the potential energy, we said it was 0, and then it gets up very high and it comes back down to 0. So it's going to do that and then come back down. This would be the potential energy. The kinetic energy, we said we started off with the kinetic energy. It's going to dip down and then it's going to come back up because we said we had a lot of kinetic energy at the beginning. We had 0 kinetic energy at the top and then a lot of kinetic energy at the end. So the red is our kinetic energy. And then the blue is going to be our mechanical energy. That stays the same the whole time. Kinetic energy plus potential energy will always be equal to that mechanical energy. This is what the energy as a function of time would look like for all of those. All right, more forces. So for gravitational force, one example of seeing that is the moon orbiting the Earth. Gravity holds the moon in orbit. Gravitational force Fg is gmm over r squared. And so for our diagram, we have the Earth and we have the moon is going around. And while we're here, I want to talk about orbits. Orbit is free fall. We still have weight. We're just in free fall. That's why we feel weightless, because we're in free fall. That's what free fall means. Electric force. So for the electric force, you have K, Q, Q over R squared, where I guess we can write these down. K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. And then G up here is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. For the electrical force, static electricity sticks balloon to hair. And so for that balloon, the best we got, and then hair kind of sticking to the balloon from a person. All of their hair is sticking to that balloon, because the balloon would be, let's say, positively charged, and the hair would be negatively charged, and those two things attract. Strong nuclear force. Strong nuclear force keeps protons stuck together in the atomic nucleus. And so in your atomic nucleus, you've got some neutrons, and you got a whole bunch of protons in there as well. There's no charge associated with that. But there's an electrically repellent force, the electric force there, but the strong force is what keeps those two positive charges being pulled towards each other. The weak nuclear force, this that holds the parts of a proton together. So inside of a proton, you have some quarks. They're held together by the weak nuclear force. When this breaks down, you get beta decay. So we have a proton turning into a neutron, or a neutron turning into a proton, based on different things that happen. Inverse squared distance. This is both the electric force and the gravitational force, but it's that 1 over r squared thing. As distance separating objects doubles, force the force is 1/4 as big. Another way of looking at it is if you have a mass here. Well, this also works with charge. So let's say you have a positive charge here and another positive charge here, a distance of d apart, and say that force is F. If we take and we half it, we get d over 2. That force now, force 2, is going to be 4 times force 1 because of the inverse square law, right? So we've got KQQ over r squared, or GMM over r squared. We double the distance, we get half quarter times the force, because we have to square it. We must square whatever we're doing to it. And then Newton's universal law of gravitation, that's Fg is gmm over r squared. This gives us weight. That's Fg, it gives us orbit. All that fun stuff. All right, so number 1 for our problems here, find the gravitational force between these two objects separated by 2 meters. So we have mass 1, mass 2, and then that 2 meters is going to be my r. So the gravitational force is gmm over r squared. Well, we know all those numbers. G is always 6.67 times 10 to the negative 11th Newton meters squared per Coulomb squared. So plugging all that in, 6.67 times 10 to the negative 11th times one mass, 1,000, 1 times 10 to the third, times another mass, 2 times 10 to the fifth, divided by the distance separating them, 2 meters, and then that has to be squared. If we're going to put that into our calculator, throw that in there. We have 6.67 times 10 to the negative 11th. Put it all in at once, and then use that second comma sign for the little EE, 6.67 times 10 to the negative 11th, times 1 times 10 to the third times 2 second E5 divided by 2 squared. Don't forget to square the distance separating them. That gives you a gravitational force of 0.0033 newtons. And so you can pause it here and try to do that on your calculator on your own. Describe the force between the two masses. The force between masses is always attractive. That force is going to pull them into each other. Find the electric force. So that's F equals KQ over R squared between two charges, 3 times 10 to the negative 6 coulombs each. So that's going to be Q1 and Q2, and then a distance, so that's my radius of 0.02 meters. So for electric force, K is always going to be equal to 9 times 10 to the 9th times one of my charges, 3 times 10 to the negative 6, times the other charge, 3 times 10 to the negative 6, divided by the distance separating them, 0.02. And again, we have to remember to square that. And so we'll pull the calculator back out. So it's 9 second, comma, to get the EE button, 9, times 3 second, comma, to get the EE button, and then you do negative 6, times 3 second EE to get that button, negative 6, divided by 0.02, and then we have to remember to square that radius. That gives me a force of 27,000 newtons. And again, you can pause right now and look at that. So that force is 27,000 newtons. And it's worth pointing out that the electric force is a stronger force than the force of gravity. It just is. All right, we're going to talk about momentum a little bit. This is also going to be on our test. So for momentum, momentum is equal to mass times velocity. This is mass in motion. One of the things that's important about momentum is that we said it was conserved. P initial is equal to P final. That means M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Or sorry, V1 initial, V2 initial, V1 final, V2 final. And so our diagram would be any object that is moving, if it has a velocity and a mass, it's going to have momentum. Impulse, that's force times time is equal to impulse. That's equal to the change in momentum. That's how an object changes its momentum. By having a force applied over a time, we get a change in momentum. Instead of a picture for that one, this would be like a ball bouncing off of the ground or something. But instead of a picture for that one, we're going to say force times time is equal to like mass times change in velocity, which is change in momentum, or we would do force times time is equal to mass times v final minus mass times v initial. Car 2 is at rest and gets hit by car 1. What happens to the momentum of each car? And then how does the change in momentum compare to each other? So when they hit, car 1 loses momentum. Car 2 gains momentum, and what we see here is that we have the same amount of momentum being transferred between these two things. That's the conservation of momentum. The net impulse and the change in momentum are the same thing. So what we need to do to be able to answer question 5 is find the final velocity of each one of these cars. So for our picture, well, we got m1 v1 plus m2 v2 equals m1 v1 final plus m2 v2 final. But they're going to stick to each other, right? So mass 1 and mass 2 are going to stick to each other and move off with the same final velocity. So they have the same final velocity. So when we plug our numbers in, let's say each car is 500 kilograms, right? So 500 kilograms times 20 meters per second plus 500 kilograms times 0 meters per second for car 2 equals 500 kilograms times V final plus 500 kilograms times V final. So 500 times 20, 10,000 plus 0 is equal to, when you add these together, you get 1,000 V final, because it's the same V final. So the final velocity comes out to be 10 meters per second. Now we know everything that we need to do. This is the conservation of momentum. For each of our cars. So net impulse and change in momentum, those things are the same. Impulse is the change in momentum. For car 1, the impulse, or force times time, is the change in momentum. So it's the mass times the change in velocity for car 1. So it's going to be mass times the final velocity minus mass times the initial velocity. So if we look at car 1, it's 500 times the final velocity, 10, minus 500 times the initial velocity of 20. And so when it comes down to it, the impulse or the change in momentum for car 1 is negative 5,000 kilogram meters per second. If we look at car 2, the change in momentum for car 2 should be the same but opposite, right? So it's going to be mv final minus mv initial. So that's going to be 500 times 10 minus 0, because initially it was at rest. And that change in momentum is positive 5,000 kilogram meters per second. Part of the conservation of momentum is that each object experiences equal and opposite changes in momentum.